about 29 petawatts of energy on the Earth's surface in any given day. Most of this solar energy is untapped. Silicon-based solar energy cells have been available for several years, but they've not quite made a dent in the market. Reason being, they're low in efficiency and have extremely high cost of manufacture. Recently, scientists have discovered a new branch of materials which are carbon-based and which can convert solar energy to electricity at the nanoscale. Due to their size, they're extremely light in weight and cost 50% less to make than the silicon competitors. In addition, you can spray paint these on a variety of substrates, including flexible and transparent. The challenge is efficiency. Right now, these cells have an efficiency of only 5%. This is because the properties of these new materials are unknown and not been studied. My research consists of studying these materials using scanning tunneling microscopy and studying their electronic properties, by studying their self-assembly and finding out different parameters which can make these structures highly ordered. Order is extremely important because the higher the order, the higher the conductivity, the higher the efficiency. And that's what my research concerns. So in the future, when you see sprayable solar batteries on your car, remember the work started here at Rice.
Okay, I want everyone to think back to a time when you were an undergraduate and you sat in a lecture hall just like the one that we're in tonight. You were in a course with other students who were very, very different from yourselves. You came from different backgrounds, you had different aptitudes, you had different educational goals. And yet, despite those differences, you all received the same course, down to the lectures that you attended, the textbooks that you used, and the homework problems you completed. And if you all remember, that one-size-fits-all approach to education didn't work for everyone. A lot of good students were held back, and a lot of struggling students were left behind. A better approach to education would be to have personalized instruction tailored to meet your needs as an individual student. The problem, of course, in doing that is that it's impossible for one human course instructor to provide that level of personalization for a reasonably sized class. To address that challenge, we have developed a machine learning propelled, statistically minded textbook that learns about you while you learn about it. This personalized learning system, or PLS, mines data from student interactions with course content and homework problems and uses this data to enable personalization at large scale. Based on what the PLS learns about you, it's able to select the most appropriate material for teaching you a new concept. Additionally, it can select adaptively the most efficient set of homework problems for evaluating your understanding. Finally, if you're struggling, it can diagnose why you're having difficulty and be able to recommend appropriate remediation. The PLS enables an educational revolution by personalizing education and optimizing for you as an individual, enabling you to learn faster, better, and more efficiently.
I work on nanoscale electronic effects, specifically developing advanced techniques for the characterization of electronic devices. This is important because the latest generation of CPUs from Intel, for instance, the cost per transistor is actually higher than the previous generation. This is a reversal of the trend of the past 50 years of decreasing costs and increasing performance. The smallest feature size on these devices is less than 60 atoms across, meaning atomic precision is crucial. New methods and materials will be required if we want to continue to advance electronics down to the nanoscale. So specifically what I work on is developing a technique called alternating current scanning tunneling microscopy. Essentially what we do is inject two offset microwave signals onto an STM junction and measure the difference frequency produced by the nonlinearities of our sample's capacitance voltage response. Essentially, we can tell the electronic carrier type and concentration with atomic resolution, giving us chemical specificity. What this means is that I can tell you where the dopants are, what they are, I can tell you where the defects are at and the type of defect, and how these defects affect conduction. And we can use this to build better nanoscale electronic devices. We also wish to apply this technique to materials beyond silicon, such as conducting polymers, nanotubes, and graphene, materials that will be important for future devices. Thank you.
trying to access your email or make a credit card purchase. Here, your main concern should be the security of your information. So Wi-Fi is like a room full of people all shouting messages at a common messenger, the Wi-Fi access point. When it's your turn, you stand up and you shout your message to that messenger, who then relays that information to the rest of the internet. Now the problem becomes apparent. Everyone in the room can hear your message. So currently what we do is something called encryption. Now this is analogous to if you and the messenger both spoke Spanish, knowing that everyone else in the room didn't. However, a smart eavesdropper could memorize exactly what you said with enough time and resources like a dictionary, figure out what your message was. Because of this inherent flaw in wireless transmissions, we need to figure out a way to keep eavesdroppers from even hearing the message itself. So what if you used an air horn? Now, if you were to blast this air horn, none of the eavesdroppers would be able to hear your message, but it would be very difficult for you to communicate with the messenger and all as well. So the ideal and seemingly far-fetched solution is, what if you and the messenger could communicate while blasting an air horn in all other directions and places? So it turns out this is possible. With with new multi-antenna 802.11ac Wi-Fi access points, they can employ a technique known as multi-user beamforming, which essentially allows for them to transmit multiple streams of data to multiple users concurrently. Leveraging this, we developed a technology called orthogonal blinding, which essentially uses one of the streams to communicate with the intended user and the remaining streams to jam. Our work represents a paradigm shift in wireless security. Instead of simply trying to obfuscate the message, we strive to keep the message from even being heard in the first place.
Imagine not, I came into this room in a cloak that makes me invisible. This is not science fiction or a movie. It could be real. In our research group, we developed an invisible cloaking device in terahertz range based on a new approach. We can place a metal coin in our device, shine a terahertz laser on it. The terahertz beam goes around this object without casting any shadows, rendering it invisible. Our device consists of two metal parallel plates. We change the plate spacing in order to manipulate the light around this object. So currently, we achieved the proof of concept in a single frequency, in a single direction, which is a great stride forward toward the real-life invisible cloaking. So this technology has a lot of potential applications in the future, like ranging from graduate students who want to hide from their advisors to military jets completing a mission without being detected.
Jason Holloway.
Video cameras are everywhere. You probably have one with you right now. Your cell phone, your laptop, your tablet. The problem with these video cameras is that they force us to make a choice. We can either have a low-resolution, high-speed, noisy video, or a high-resolution, low-speed, blurry video. And today I'm going to tell you how we fix that problem. Using the cameras that you have in your pocket right now, I can give you a high-speed, high-resolution, clean video. All that I require is access to your shutter, the thing that lets light into the camera. If I can open and close that many times as I capture each frame, if I can flutter the shutter, then I can layer incoming light. It kind of looks like you've taken two exposures using a film camera. So I layer light in a very specific way, and because I control the shutter, on the computer afterwards, I can undo that layer and give you a clean video out. The elegance of our technique gives us rise to a broad application space, where we can go, we could develop a third-party app for a smartphone to make your phone record video 10 times faster, fast enough to stop motion. Or we go to the complete other end, government agencies, defense agencies, and download videos from spy satellites 7 times faster. The thing I want you to remember is that Fluttershy can take low-tech, common video cameras and give you the output of a high-tech, expensive video camera. Thank you.